Okay, for the next couple of classes, we're going to talk about volcanism and volcanoes. It's one of the geologic hazards that we have that affects a lot of people on Earth because of where people live. Most people live in coastal regions, and as it turns out, volcanoes are found in coastal regions as well. So just to kind of put this in a bigger perspective, we'll talk about different rock types this semester. We're not going to talk about them in the same detail that you might get in a regular geology class, but we'll touch on some of the topics surrounding that. The volcanoes are part of a rock system called igneous rocks, and these are all formed from solidifying magma. This is probably stuff you remember back from middle school. We also have sedimentary rocks that can form from the breakdown of pre-existing rocks. Those rocks that break down can either be igneous or other sedimentary, or the final type, which we'll talk about in a minute, metamorphic. So they occur and form on the Earth's surface. I happen to like igneous rocks, obviously, because I study volcanoes, but I think most people find sedimentary rocks a little easier to understand, and that's because sedimentary rocks form in the same environment that you're used to, the Earth's surface. Igneous rocks tend to form mostly beneath the surface. These are called intrusive igneous rocks. Only about 10% of the magma that's produced on Earth ever makes it to the surface. When that happens, you can get volcanic rocks. But even those are very odd environments for most people. Very few people get to see a volcanic eruption and then get to really witness the rocks that form from them. Metamorphic rocks are those that form by changing a pre-existing rock. You can change a sedimentary rock into a metamorphic rock. You can change an igneous rock into a metamorphic rock, and you can even take other metamorphic rocks and metamorphose them further and change those as well. So these are rocks that change as they come in contact with heat and pressure and different fluids within the Earth. And these are probably the hardest to understand because all of this happens well beneath the Earth's surface. At least with some igneous rocks, they form on the surface. We're not going to spend time looking at rocks in particular in this class or lab. If you take a physical geology or general geology class, you'll get some experience doing so. Lots of different igneous rocks out there. The one I have there is a volcanic glass called obsidian. Forms when lava cools very, very quickly. Sedimentary rocks can take on many shapes and forms. This particular rock that you see here is a conglomerate. Some rounded, smooth pebbles that are cemented together with smaller particles, indicative of a river environment. And then metamorphic rocks tend to be the ones that have these really strange fabrics where minerals, because of the heat and pressure, are forced to align with one another, and then they can be twisted and contorted. Okay, but we're going to start with the volcanic rocks. And what we'll do with this chapter, and it's kind of a similar format to what I'll follow with lots of other chapters, is that we'll talk about kind of the sciencey things first and then get into how humans are affected by these processes. So this first little section here will actually bring us back to a lot of the topics that we talked about in our background section. So in order to understand what magma is, you really have to look at each little detail of what's in it, different components. Magmas consist of many different things. I mean, the most obvious thing is that it's melted rock, but in particular, it's a melted certain kind of rock. In fact, for the most part, vast majority of all magmas consist of melted silicate minerals. And if you remember back to our chapter on minerals, we talked about what a silicate is. Remember, a silicate mineral is one that has silica tetrahedron in it. Silicon in the middle, 4 oxygens surrounding it, and those tetrahedron can bond together into chains and sheets and frameworks. And those bonds are really strong, right? Remember we talked about how strong those bonds are? In order to break those bonds, you have to have a lot of heat. That's why magmas are so hot. So when you break these down, what's interesting about it and what most people don't realize is that in order to melt a mineral, let's say we have something like this. That would be a chain silicate, where each of those triangles represents one of those tetrahedron. They were linked together in a chain. And remember, the bonds that hold each of these tetrahedron together are really, really strong. So you start adding some heat to this. That whole molecule starts vibrating faster and faster and faster. At some point, what will happen is that you can start breaking bonds. You might break that bond. You might break that bond. The more heat you add, the more broken down these silicates will become. If I add more heat, I'm going to break another bond. How do you think this changes the behavior of the magma? By adding more and more heat to it. Do you have to break every bond to get it to melt? No, you have to break a few of those, right? And the more heat you add, the more of those bonds you're going to break. How is the magma going to behave differently with breaking more and more bonds?
It's going to flow more.
It's going to flow more easily. Yeah, so it's a viscosity. You've probably heard the term viscosity, right? What does that term mean to you?
If it's more viscous, it's more like not fluid, and if it's less viscous, then it's like water.
Yeah, viscosity and fluidity you might think of as being opposite terms. If something has a high viscosity, it has a low fluidity. And if it has a low viscosity, it has a high fluidity. So when you heat this higher and higher and higher, you break more and more bonds, you lower the viscosity and make it more fluid. And that has a huge effect on how your volcano is going to behave. Yeah?
Isn't it true that glass is just like a very viscous liquid?
Yeah, that, I don't think I have a sample in here. I'll bring some next class. So in the previous slide, I showed you that photo of a volcanic glass called obsidian. What's interesting about that is that it's technically on a molecular level a fluid. What's a fluid? How does a fluid differ from a solid?
Its molecules are able to move around more freely.
It's move around relative to one another. And in fact, what happens is you have a magma, like in this case, where some of the bonds are broken, and those little partial molecules can move relative to one another, and you cool it super fast. You cool it so fast that bonds can't form. And what will happen over time, and it takes really long time for this to happen, is those little partial molecules can still continue to move. So when you have a glass pane like you have over here, in fact, they've shown this like out in the eastern part of the United States in churches that were built back in the 1700s. You have these long panes of glass, and if you look at the very top of the pane, you look at the very bottom of this like 300-year-old glass, the bottom's thicker. And what's happened over time is that glass is slowly moved. Now, if I took that chunk of obsidian that you saw in that previous photo and I whacked you over the head with it, would you say it's a solid or a liquid?
Solid.
You'd say, damn, that feels like a solid to me, right? Well, and that's kind of the rub on how we define things. From a molecular level, it's a liquid, okay? It's a liquid because those molecules can move. But it behaves brittly like a solid. If I took a hammer and whacked it, it's going to shatter, right? Like a solid would. Well, that's because those molecules cannot flow fast enough when I hit it with a hammer to get out of the way, so it shatters. So on a behavioral level, it behaves like a solid. On a molecular level, it's a liquid. It just can't respond very easily to stress, so it tends to break. In order to flow, you have to give it hundreds of years. So it comes down to how fast you deform it. If you deform it super slow, it can flow. If you try to deform it really fast, it's going to break. So it's interesting stuff from kind of a material standpoint as well. But again, the main point is the more you heat it up, the more bonds you break, the more fluid it's going to be. And that's going to play into everything we talk about from this point forward. So if you can understand that little diagram right there, add more heat, you break more bonds, you make the lava more fluid, you're 90% of the way to understanding why volcanoes do what they do. Okay? So let's kind of continue on with this. So you have in a magma, it's mostly melted rock, but it's not all melted rock. Magmas actually have 4 different things in them, 4 components. So they have these melted silicate minerals. There's also, if you're able to actually go up, if you were in Hawaii and you saw that red runny lava, most of it's melted silicate mineral. But if you're able to look super close, you would actually see some little tiny green minerals in there that are still solid. Those are called olivines. And this isn't working. Let's try that. And in fact, let's say you have a magma that's 1200 degrees centigrade. Just about everything melts at that temperature, except for one mineral called olivine. It has a melting point that's higher than the magma temperature. So it can't melt. It's not going to be melt. It's going to be solid. But most other minerals, minerals like quartz, feldspar, their melting points are down around 800, 900 degrees C. So I'll give you an example. Let's say you have a magma temperature of 1,000 degrees. Now to you as humans, that's really hot. If you touch it, it's going to leave a mark. I've touched it. It leaves a mark. But it's not hot enough to melt all minerals. Some minerals are stable at those temperatures. Olivine melts around 1,200 degrees. You're not even close to melting this. You have to raise the temperature 200 more degrees to melt that mineral. So if it's present in your magma, it's going to exist as a solid. No problem at all. But other minerals like quartz that melt at 700 degrees, well, you've exceeded their melting point by 300 degrees. They're a liquid. You've broken most of those bonds. That stuff can flow around just fine. What if you threw water in there? Boil. Yep, it turned to gas. And that is our next component. There's lots of things that at 1,000 degrees won't be a solid, won't be a liquid, but instead will be a gas. What do you guys know about volcanic gases? If you go to a place like Yellowstone, old volcano, lots of volcanic gases there, right? How do you know?
You can smell it.
You can smell. What do you think is the most common volcanic gas?
Sulfur.
When you go to volcanoes, that's what you smell, right? Sulfur. And there's a lot of different sulfur compounds. There's H2S, there's SO4, there's all these different sulfates and sulfites and sulfides. Lots of sulfur gases. But as it turns out, that is not the most common gas that comes out of a volcano. It's not even close. Want to take a guess to what is?
Hydrogen?
It's got hydrogen in it.
H2O?
Yeah.
Oh.
Actually, yeah, the most common volcanic gas is water. 90% of all the gas that comes out of most volcanic eruptions, water vapor. That's the origin of our oceans. Back when the Earth was really, really young, covered by volcanoes, those volcanoes mostly pumped water into the atmosphere, and it condensed and formed our oceans. But there's a lot of things that are in volcanic gases. Sulfur compounds, carbon dioxide, carbon monoxide, dozens of different gases. So if you have magma temperature that's 1,000 degrees C and you have something like water where its boiling point is 900 degrees lower, water is going to exist as gas. So if you're there on a volcano, fumarole. Fumarole is a little gas pit. You see all the sulfur compounds sublimating around that fumarole, right? And you see all the white fume. Most of that white fume is actually water vapor, though. Just a very small percent is sulfur. And finally, the last thing that we find in magmas are something called xenoliths. If you break that word down, you might be able to guess what it is. What's a lith?
Rock.
A rock. Xeno. You've heard of lots of political talk this year. You've heard of xenophobes, and these are things that are different, right? These are, for lack of a better word, these are hitchhikers. These are rock hitchhikers. They're little pieces of rock that the magma takes and grabs a hold of as it moves from the upper mantle up to the Earth's surface. So solid rock fragments picked up by magma as it travels to the surface. First day of class, I told you I had a piece of the mantle in my office, right? Even though humans have never drilled to the mantle, I have a piece of it just 50 feet from here. That is what's called a mantle xenolith. It's a little piece of the mantle that magma picked up, dragged up to the surface. So they can give evidence about the rocks that lie beneath the volcano. Rather than drilling down, trying to figure out what might be there, you can just look at lava flows that the volcano produces, and you can find these little xenoliths. Most lava flows have somewhere between 2 and 4% xenoliths in them. If you look at any lava flow and look at it long enough, you'll see these little rock fragments. It tells you what's beneath the volcano, so it can be very informative for geologists about what lies below. Okay, so magma has 4 parts, 4 components. Liquid rock, which means melted silicate minerals. The hotter the temperature, the more melted it is, the more fluid it's going to be. We'll have solid minerals, whose melting points are higher than the magma temperature. We'll have gas, which is maybe one of the most important components because it really determines how the volcano is going to behave. And those occur when your boiling point is lower than your magma temperature. And then you have these xenoliths, these little rock hitchhikers. So there's a little photo right there. The black is the actual magma that's then cooled. So this is the melted silicate material. After the volcano erupts, it cools off and forms rock. And this right here is your little mantle xenolith, the little green material. So that actually came from the mantle. Okay. Why do we study volcanoes? There's actually lots of reasons. Obviously, volcanoes pose a hazard as we talked about earlier, to a large segment of the Earth's human population. Volcanoes tend to be found in coastal regions. People tend to be found in coastal regions, so there's a lot of overlap between people and volcanoes. Volcanoes are hot, and because of their heat, they can be used as a potential energy source. Geothermal energy is something that humans use. We don't use it a lot, but some countries use it more than others. New Zealand has a lot of geothermal power that they use. Iceland. There are some geothermal plants here in the United States. There's a couple in California. Anywhere on Earth where you dig down, you can find that the heat increases as you go down. So everywhere has the potential to use geothermal as an energy source, but few places are using it. We just don't have good technology yet to exploit it. But we could. We talked about this in our mining chapter last week. Most of the Earth's profitable mineral deposits, ore deposits, remember ore deposit is any profitable rock unit that you can dig up and sell in today's economy. Most of those are found in volcanic regions. Something we're not going to talk a lot about in this class, but if you take a geology class, you'll learn more about it. Mass extinctions. When you look at the fossil record and how life forms have changed over time on Earth, geologists have noted that there are abrupt changes in the number and forms of life at different times in the geologic past. You have a certain assemblage of life forms, and suddenly they change in the rock record. You have lots of dinosaurs. And then 65 million years ago, suddenly no dinosaurs. There appears to have been a mass die-off of different life forms that are then replaced by others. It's not just the dying off of the dinosaurs, that's the one you hear about the most. There's been dozens of mass extinctions. In fact, the most recent one was about 12,000 years ago. Very recently geologic, at the end of the last ice age. We used to have things like mammoths, saber-toothed tigers, different types of camels in North America. They all went extinct, and not that long ago. There's a lot of different reasons. Not all mass extinctions have to occur for the same reason. We think most likely the dinosaurs were wiped out by a meteor 65 million years ago, but many of these other mass extinctions that have taken place may be due to other reasons, and volcanoes may be one of these reasons. The idea is we have one large eruption or many eruptions that occur at the same time, alter the atmosphere to the point where some life forms can't exist and others can. So we know it's an agent of atmospheric change. Mount Pinatubo lowered world temperatures by a couple of degrees for several years. Remember, Pinatubo wasn't that big of an eruption. There's been others. El Chichon in Mexico, I believe in 1985, lowered world temperatures for 2 or 3 years. So we know these can have a profound effect on the atmosphere. And if the atmosphere changes, things like growing seasons will be affected. So they can obviously impact people and other life forms. I'm interested in them kind of for reasons that aren't as practical. I've been studying volcanoes for most of my adult life, and I would love to say I do it because I want to save lives and because I want to make the world a better place. But I'd be lying if I told you that. I actually study them for the last reason, is that they're really cool. But I like the fact that they're prominent on other planets and bodies in our solar system. If you go to the moon, if you look up at the moon, big full moon on a nice night, and you see all those dark areas, those are all lava flows. Massive lava flows, just like the kind we have in Hawaii. If you look at Mars, we already looked at Mars a week or so ago. You saw the massive volcanoes that are there, some of the size of Colorado, 90,000 feet high. Venus is completely covered with volcanoes. Mercury covered with old volcanoes that have been pulverized by meteors. So if we can understand volcanoes here on Earth, we at least have a start on understanding them on some of our nearby planetary neighbors. So what we'll do now is we'll kind of look at how volcanoes behave. Not all volcanic eruptions are the same. Some are very violent and explosive. You saw the Mount Pinatubo video where you had those big ash columns that were blasted up to 100,000 feet. But if you go to Hawaii, that's not the kind of activity you see. You see these red runny lava flows. Why do you have different volcanic eruptions in different places? Well, to get to answering that question, we kind of have to understand how a volcano is put together. And the very source of the lava in most cases is something called a magma chamber. This is the subsurface holding area for all the different material that gets erupted later. And they're different in different places, and they're different on different volcanoes. The magma chamber that's under Yellowstone is almost like a giant ocean of magma. It's down about 3 miles. It's about 60 miles wide, 5 to 10 miles deep. It's huge. It's this huge cavern of melted material. But if you go to Hawaii, completely different. Hawaii is just a bunch of cracks in the rocks that hold liquid material. Some of them are really narrow, a few centimeters. Some of them may be a few meters wide. Biggest ones are probably as wide as this room. But hundreds of cracks, and the lava sort of fills them. So they can be very tiny. Just a series of interconnected cracks that the magma is kind of working its way through as it travels up to the surface. Or they can be enormous. One in Yellowstone, 40 to 60 miles wide perhaps. This diagram is, it's all right.